My name's Correll, Director of Product Management at Aerohive, and might as well do a little bit of my background. I've been in Wi-Fi for about 15 years, worked with the controllerless stuff, the controller stuff, and even a little bit of the virtual channel stuff. Going back before them, my networking days actually goes back about 30 years to the early days of Cabletron, thicknet cables, all the way through Ethernet switching, a little token ring, a little FDDI, a little ATM even. And the RF days actually go back to the 70s, working airborne radar systems. So got a lot of experience with RF and Wi-Fi and networking over the years. So it's kind of fun to be up here and talking about 11AX. Specifically, I'm going to talk about OFDMA, and obviously you guys all know it's Wi-Fi certified 6 now. So we talked a lot about 11AX over the last couple days, and everybody here has read stuff about 11AX over the last year or so. So, you know, I like to have you guys do some work here instead of just me. So what are some of the fancy, shiny objects, the technologies, the components that make up 11AX? So you guys got to work. What? BSS coloring. That's really, really cool. The idea I don't have to wait for other people to talk. That is really new and neat, right? Nah, it's been 11AH for a long time. So it's not really new. So what else is new with 11AX? OFDMA, that's actually the most important one, at least to me. I pulled this out, and we all know there's a lot of literature, a lot of marketing stuff about OFDMA, so I like to go to other documents, and this is EDN, Electrical Design News, and they're talking about OFDM, new technology, takes fixed access wireless, separates the channels up, allows different people to talk at different times. That is really, really cool. But this is from April 2007. So OFDM is not really all that new. If you think, or OFDMA is not really all that new if you think about what's going on. As a matter of fact, most of your phones probably support it for LTE. So what else is new? What? Target wake-up time. That's a neat thing, especially for IoT or your phones wearing the batteries out. That's going to definitely, wait a minute, that's 11AH too. That's not new. Anything else that's new? Uplink multi-user, that's really cool. The MIMO stuff came out of 11N. The downlink came out of 11AC. Multi-user MIMO uplink won't be available till Wave 2. That's not really all happening yet. Anything else? Longer symbol time. That's really, really cool. I can stretch out the symbols. So instead of like a 4 microsecond, I'm out to 16 microsecond. I can talk to longer distances and go way out. I got a Doppler bit so I can adjust for that function. What, Keith? Yeah, that was in 11P. Not all that new. Anything else? Come on. You guys are smart. You've been reading these books? 1024 QAM. Thank you very much. It's going to go faster than we can believe. You know, well, maybe if you're sitting on the AP. But I need negative 35 dB to make that work. Well, maybe if I have smaller channels, I have less noise. No, but it only goes down to 20 megahertz channels, so I can't get any smaller. So I guess it's not really that neat. Anything else? The letters at the I'm not going to go there. What about multi-BSS? What about if I can send out one beacon, which would have all my BSSs, all my SSIDs listed in it? Wouldn't that be cool? That's in 11AX. It was also in 802.11-2012. Anything else? No, but the whole purpose is a lot of this stuff people are talking about is brand new technology, it's bleeding edge technology. Am I ready to make this leap of faith to it? Most of the stuff is not brand new. Most of the stuff has actually been for a while. It's just being incorporated into another new standard, new certification. And by the way, they're already working on the next generation one. So what are we going to talk a little bit about here today? 802.11, first thing people want to understand is what's really happening with it. The IEEE, we're actually in draft 2 right now. You know, as I think David mentioned the other day, they're up to 682 pages. Crazy type stuff. Has anybody ever read any of those documents? I thought I'd actually do that, just so you guys know how much fun it is to sit in IEEE meetings and listen to this stuff and vote on this stuff. In the HE-SIG-A spatial reuse value 15 allowed subfield, the SR control field, the most recently received spatial reuse parameter set element from the associated AP is equal to 0. The station cell set the TX vector parameter spatial reuse of any HE PPDU to SRP underscore IND underscore non. This is nuts. I had to read this thing about 15 times to understand what it was actually saying. So one of the things I want to mention, if you guys really want to know about OFDMA when you get out of here, It's a really good white paper from Rhodes and Schwartz, and I highly recommend reading that. So it's important to understand what's going on in the industry. But the IEEE is going through. We're at draft 3 right now. Pretty much by next year, they'll come out with the final standards sometime in Q4, and that's kind of where we are right now. Wi-Fi Alliance, at the other hand, they just want to rename this to Wi-Fi 6. It's an ongoing PlugFest. As a matter of fact, right now, as we speak, they're doing a lot of PlugFest testing. They have about 7 PlugFests. They're in the 5th one right now. They're about interoperability. Is this stuff all going to work together? And how's it going to work together? Obviously, they've launched their marketing program, and it's identified as Wi-Fi 6. A lot of good things happening there. And one of my roles is I actually sit in on the IEEE and sit in on the Wi-Fi Alliance meetings. And it's important to understand that why this takes so long, it's not because they're trying to figure out the technology. They're all kind of trying to come into agreement of what's going to be in the standards, what's going to be in the certifications. Has anybody ever sat in an IEEE meeting? You're in a room, you got 250 people, got a bunch of microphones sitting around. There's 8 guys around a microphone over there arguing that in this sentence, the word shall be used in reference to the AP. And over here, you got another 5 guys saying we should use the word should. And after about an hour debate, you vote on it. And it's like 8 for shall, 7 for should, 256 abstain. That's why this stuff takes a while for this actually to happen. It's really important to understand that. So what about products? Products are out there. Products are shipping. Products are available. And we'll talk about more of that as we go along. It's important to understand this is a very transformative year for Wi-Fi. 2018, if you actually look what's happened over the last 10 years, where we've gone in throughput and performance, the Wi-Fi Alliance just released a study the other day that says it's about $2 trillion worth of economic impact with Wi-Fi. And that's going to double in the next 5 years. So it's not going anywhere. 5G isn't going to replace it. It's going to be around for a long, long time. Oh, by the way, WPA3 is a prerequisite for 802.11ax, and so is something called Agile Multiband. If you don't know what it is, go to the Wi-Fi Alliance, download a paper, and find out more about it. IoT is going to be a big impact. Obviously, there's a lot of other technologies, but there's also an impact in 11ax, and then obviously 11ax is huge. At least in my mind, it's huge. And it brings the question, is 11ax Wi-Fi switching? We heard of this a couple times today. What do you guys think? Is it Wi-Fi switching? You guys are quiet. Come on, wake up. I'm shaking heads, but I'm not hearing anybody say anything. Well, maybe. Who said hell no? Good there. Well, maybe. It depends. 42, whatever you want to look at it. But what do you think? What do you think about it? And sometimes it's good to get like independent opinions. It didn't work. It didn't work. Want to try it again?
It's a Wi-Fi switch. It's a Wi-Fi switch.
You see? So we're done. It's been settled. In case you guys missed it the first time.
It's a Wi-Fi switch. It's a Wi-Fi switch.
We don't have to discuss this anymore. If Devin agrees with me, we're done. We'll talk more about this at the end. But it's important to understand what's happening with Wi-Fi and understand what's going on, because we've caused ourselves a lot of problems. And by we, I mean vendors. Because if you look at the evolution of Wi-Fi, about every 3-4 years, we go up to our partners and we go out to customers saying, God, I got this brand new technology. It's faster and it's so much better, and it's called 11G. And then 3 years later, we got 11A. And then we got 11N150 and 11N300 and 11N450, and we even promised 11N600. Nobody ever got there. But then AC Wave 1 came along, and AC Wave 2 came along. And if you actually read the standards for 11N, it was called high throughput. A couple people have mentioned that already. And if you read the standard for 11AC, it was called very high throughput. You know what 11X was called? High efficiency. Yeah, it's faster. Yeah, some way with magic numbers, I can get up to 10 gig worth of throughput. And if somebody's telling you to go to 11AX because it is you 10 gig, just smile and nod and realize they have no idea what they're talking about. Yes, it will go faster, but the value of 11AX is high efficiency. And that's why it's actually called that. And if you want to get really scared, they're already working on the extremely high throughput version. So if everybody never does, 180 megahertz wide channels. Wait until they get 320 megahertz wide channels and 16 by 16. But that's a different discussion at a different time. But this is what's happening. This is the continual evolution. The problem was, You know, we get a little bit faster, we tweak a little things. This is just kind of a slide for the nerds in the group. You can kind of look through them. But this is important. It's important to understand how Wi-Fi actually works. And hopefully everybody in this room knows that what happens when I want to talk to a bunch of people, I'll talk to you, you'll give me acknowledgement, and then I'll talk to you, and you'll give me acknowledgement, then I'll talk to you, and you'll give me acknowledgement. And this worked really, really cool. 11A, 11G, and it said, you know, this is good, but we want to make it better. So we went to 11A, and all we did was we made it faster. We still had the same inefficiency. We still had the same issues of, I need to talk to one person at a time, I need an acknowledgement, I need to go through that, but we sold it. Then 3 years later, we came back and said, I got something brand new for you. It's called 11AC, and it's even faster. But it really was still very, very inefficient. So we had to improve it. We had to do something better, because this is the problem we still had. We're doing a bunch of road shows right now, and every city we go into, they all identify that as a different road, because they all got that road. And the thing about this, if you look at the side, and I think that's the 405, actually. I think it's by the Getty Center or whatever. But if you look on the side of that road, there's a speed limit there, and it says 55, and they're all going 12. And if I raise that speed limit to 110, they're all doing 12. If I went up to 200, they're all doing 12, because you can't do it. You got multiple different types of traffic, people that don't know how to drive, older devices, whatever, it's going to be slow. This is what we want to get. We want to get into an environment where everybody gets what they need. And that's what 11AX is all about. That's what OFDMA is about, because this is what we want to see. That's cool. How many people I got in this room? Count it up real quick. I got about 150 people in this room, which means with 11AX, I could talk to every one of you with 2 transmit opportunities. In theory, never work in real life. But theoretically, I could talk to 74 people at one time with 160 megahertz wide channels. Once again, we know that's never going to happen. But the whole idea is it's more efficient because I can talk to more than one person at one time. So this is a poster. Who's the guys who like to read the IEEE specs? There's 1 over there, 2 over there, 3 over there. Get a life. But it's important to understand, if you actually read through those specs, there's actually 72 new features within 11AX, within the standard. These are the 7 shiny objects. These are the ones that people talk about. We just talk about preamble updates. Great. I'll talk a little bit more about that. Longer frames. That's cool. It actually gives a lot of advantage to outdoor use. QAM, 256 up to 1024. That's where I get that 9.6 gigabits worth of throughput. It's 25% more efficient than 11AC Wave 2, but it has a high SNR requirement, so there's going to be some value. Target wake-up time, yeah, in the IoT world, it's really cool. Overlapping basic server set, that's going to have a use. Multi-user MIMO, what's cool though is OFDMA. And that's the one I think is going to have the biggest impact on anything. That is going to be different, but it's not a brand new technology. It's not bleeding edge stuff. It's been used since 2004. It's been used in 802.16 WiMAX, G3, G4, LTE. The functionality is there. It's been tested. There's test equipment for it on the wireless side, just not on the wired side. And also 2.4 is back. Nobody's excited about that but me. It's 3 or 4 usable channels. Take advantage of it. Imagine multi-gigabit speeds, OFDMA with 2.4. It's exciting. Maybe not. Too many frames. Okay, PPDU formats, just got to do a little bit of the nerdy stuff here. There's 4 different new PPDU formats. There's 2 for single user, and there's 2 for multi-user. The HE, that's high efficiency single user. Basically, you got the same stuff you saw. You've got the legacy training fields. You've got a repeated legacy training fields. It's really efficient, and it's really robust type functionality. Then you've got the high-efficiency multi-user. This is how I send a trigger frame, or it's actually send traffic from the AP to the client. High-efficiency extended single user. This is where I can talk to somebody further away. What I'll actually do is I got a longer frame, stretch it out, make it more robust, longer guard interval. I actually boost up the training fields by 3 dB, so it gets there a little bit further. I can actually duplicate this on 2 separate channels. Once again, it's designed to work outdoor, more robust at a greater distance. And then the key one, the high-efficiency trigger-based one. This is when I generate, and you're going to love triggers. I generate a trigger to make things happen. There's actually 7 different types of triggers, but once again, a lot of them beyond the scope of today's presentation. But in order to talk about OFDMA, we need to talk about OFDM. And hopefully all you guys are experts on it. You read all the chapters. What chapter is that in, David? Just make one up. 7, good. What it actually is, it's a digital modulation technique. The whole idea is I've got all these sub-channels, but the clients use all of them. I allocate the entire spectrum of subcarriers for a fixed amount of time to a single user. And the next transmit opportunity, I send them to somebody else. So this is what it looks like. Hopefully none of you guys think that that 20 megahertz is one signal. It's actually a bunch. If you want to get technical, it's 64 subchannels that kind of fit within that 20 megahertz channel. And if you want to get a little bit deeper, this is kind of what it looks like. Out of those 64 subchannels, I got about 56 usable subcarriers, got some pilots. Does anybody know what a pilot is? It's really cool, because what happens is you stick these pilots in among the data, and I know exactly what that pilot signal should be. So when it gets to me as a receiver, I can look at how much those pilot signals were degraded and assume the rest of my signals were equally degraded. So it actually helps me recover the signal a lot better. And there's some smart RF engineers working on this stuff when they did that. But the whole idea is I got about 52 channels worth of data, break it all out, and when I go to talk to somebody, when I talk to you, I use the whole channel. And maybe you've got a big data to send, but then when I talk to you, maybe you're just doing voice. Maybe you just need a little. You still have to get that whole channel. So everybody gets a whole channel. Very inefficient. So this is the way it works. We saw this already. I talk to you, I talk to you, I talk to you. There's got to be a better way. There is. We call it OFDMA. And the whole idea is I allow multiple access, or what Devin calls switching, to occur by assigning different subsets of carriers to individual clients. And this is cool. Why this is cool is because each one of those clients that I talk to, they don't have to get the same amount of data. They don't have to get the same amount of bandwidth. They don't have to get the same MCS rate. They don't even have to get the same power levels. So what I can do with some of these clients further away, I could say, hey, you got a smaller size, lower data rate, but transmit at higher power. And somebody close, I can say, reduce your power. So as long as my EIRP balances out for that region, I have a lot of flexibility. And that's the cool thing about it. So how'd I get there? First thing I did is I took those 64 sub-channels and I made 1/4 the size, but then I quadrupled the number of them. So I still got that same amount, but it's much more efficient. I got a much more capability. I can split the traffic up in really neat ways. And what I do is I create these things called resource units. Got a question for you guys. I was talking to actually the CEO of my company a while back, and we were talking about, he was asking me about resource units, and I explained him, and he goes, well, what do we call them? And I said, resource units. He goes, don't we have anything fancier than resource units? I said, no, they just call them resource units. What do you guys think if we rename these right now to ether channels? Some of you are too young to remember that, but that actually Calpana and then Cisco copyrighted that. The copyrights run out. Let's just call these ether channels and have CWNA copyright that, because it's ethereal. Anyone know what ether is? It's a theoretical medium that all RF energy runs across. So Ethernet was actually a misnomer. Wi-Fi is a better thing for that. But, well, never mind. We'll talk about that later. But the whole idea is I can break up that 20 megahertz channel into different subgroups, and each one of those subgroups I can assign to a different individual for one transmit opportunity. So right now I can send the entire channel 20 megahertz to you. The next time I can spread it between 9 people. The next time I can spread it between 4 people. The next time I can spread it between 6. So every time I have a transmit opportunity, I can do it differently. I can give the people, or the devices, the applications, the resources, the type of information they need. And that's really, really cool. And this is only a 20 megahertz channel. If I did a 40 megahertz, if I got 20 megahertz and I can do 9 channels, how many can I do with 40 megahertz? Not a trick question. 18, thank you, this is not tough. Okay, so if I can do 18 with a 40 megahertz channel, how many can I do an 80 megahertz channel? Thank you, 37, sorry, that was a trick question. And then I can actually get up to 74 channels with 160 megahertz wide channels, which we all use every day, right? No, we don't. But it's important to understand that's the way it was designed to do. And so now I can set this up and I can do it different. So if I'm using 20 megahertz channels, 40 megahertz channels. The key point about this also is every one of these resource units, I can say how wide they're going to be, how much bandwidth you need as a client. I can do that based on lots of different things. I can purely do it on how much data you want to send, or I want to send to you. I can do it based on some quality of service thing, or I can do it based on some proprietary airtime fairness type algorithm that I use. So it gives me a lot of flexibility, a lot of functionality on how I can actually do this. And that's the cool part about this. This is kind of what it looks like for the techies. So if you drill down in there, that's a 20 megahertz channel, and I start from that center frequency, and I go left and right, and I identify frequency ranges. So as you can see, it's -22, -48, -90. And that's kind of important because I use this information to tell the receiving clients where to look for your data. It's not just, here's a chunk of data, go find it. What I'll actually do is tell individual clients, this is the space you have, and this is the space you have. If I want to go up to an 80 megahertz unit, it gets a little bit more convoluted, a little bit busier. But let's just be honest. Is this ever going to happen? I hope. You hope not. Guess what it is? This is a real spectrum trace. They work. And as you can see, each one's got different power levels. It actually does work. This is an 80 megahertz channel, not using all the resource units. And I'm going to explain to you why I'm not using all those resource units in a little bit. But the whole idea is this functionality works. It's available today. Does anybody know how many available 11AX clients are out there? Commercially available? None. But we'll talk more about that at the end. We've actually got some neat stuff that we do it with. So this is kind of what it looks like. And also, when I'm telling a client, I'll go through that whole process very shortly. When I'm telling a client, I've granted you access. I've granted you access that I'm going to send you information, or I'm granted you access that I'm going to allow you to send me information. I identify where in that spectrum, where in that 20 megahertz, where in that 40 megahertz, where in the 80 megahertz, your information is going to live. And I actually do it in a couple ways. I actually do it at the PHY layer. I actually use the SIG-B field in the PHY layer to do it, or I actually use it in the user information field. So I'm actually telling them multiple places where their data is going to be. And so I'm saying you're going to have resource unit 1, it's going to be -121 and -70, or that number at the bottom kind of is an easier way to say where that's going to be. But I identify the fields and the carriers of where that's going to be. So how does this all work? Give you an example right here of what it would look like talking to 3 different devices. So the top one is normal today, OFDMA. I'm the access point. I've got data that I want to send to 3 different people. I'm going to contend. Hopefully I get the error. What I'm going to do is I'm going to send you data, and you're going to send me acknowledgement. Then I'm going to contend again. I'm going to get the error. I'm going to send somebody else the data. They're going to send me acknowledgement. Finally, I'm going to contend for a 3rd time. Hopefully I get the error, and I'll send you the data, and you'll send me an acknowledgement. What OFDMA does is a similar type thing. I'm going to contend. I've got data that I need to go out to 3 individuals in this room. I'm going to contend, and then I'm going to decide. I've already decided who I'm going to send this information to first. So I'm going to send out a trigger frame. That trigger frame is going to go to those 3 individuals and say, hey, dudes, I got data for you. Can you accept it? And it's kind of like a request to send. Those 3 devices are going to send back a clear to send. Then I'm going to send the data. They're going to send a block ACK. Pretty simple. This is kind of what it looks like, a little bit more drawn out. AP controls the medium. I send a multi-user request to send to the 3 or 4 or 5 or 10 or 100 different devices that I'm going to send. Well, not 100. 70 different devices I'm going to send it to. They reply, basically, the transmit opportunities for this whole period. And I send a block ACK. So let's look at it this way. I got an AP. I got information for 4 different clients. I'm going to send a trigger frame. Trigger frame is going to go out. It's going to tell those 4 clients, hey, I got data for you. Are you willing to accept it? Thing goes off. They're going to send me back a clear to send. As soon as that happens, I'm going to send the data. And they're going to send a block ACK. So what it looks like is this. The trigger, and once again, there's multiple triggers. There's a trigger to wake you up. There's a trigger to block ACK acknowledgement. There's a trigger to see what kind of buffer information you got. There's a lot of different types of trigger. But I send the trigger. I identify what devices I want to talk to. Those devices confirm they're ready to receive the traffic. I send the traffic to them, and I got a block ACK. So what happens is now it looks more like this. I can talk to 1 person. I can talk to 5 people. I can talk to 1 person again. I can talk to 3 people. However I want to do that. And this is where I get that. But what about the other side? Downlink, heck, they've been doing downlink, multi-user MIMO. But what about uplink? How do I figure out, how do I let all these guys in this room send me data? And that's the cool part, because the AP still controls the network. The AP is still in charge. But the one thing I have to do is I've got to find out who's got data to send. And there's two ways I can do this. One is I can explicitly ask. Has anybody got any questions? Put your hands up. Fake it. Or you can just raise your hand anytime you want. And that's what it does. There's an implicit and explicit way to do that. The access point can actually send out a type of trigger called a buffer status report poll. And you guys are going to tell me, hey, I got data to send. This is how much data I have to send. This is the quality of service of the data. This is the access category. So then I can make decisions who gets to talk first. There's also an implicit one where anytime you send me a packet, with that packet, you can append another thing, or you can update in the QoS field that I've got data to send you. Obviously, that's much, much more efficient, and we'll see how that works. So this is kind of the whole thing. If you think about it now, first thing I need to understand, who's got data to send? So who's got data? Who's got a question? I'm not going to answer it, but who's got a question? Put your hands up. Okay, so 5 or 6 people, they have a question. Basically, you're going to tell me how much data you have to send, the quality of service of the data, the bandwidth, and all that. Then I'm going to make a decision who gets to go first. That decision could be based on just QoS, just on access category, which is pretty much all the IEEE and the Wi-Fi Alliance are looking at. But I could apply my own rules. Maybe yesterday, Jason's presentation, talking to, might have another access point that I'm doing a mesh connection with. So I might want to dedicate them a certain amount of bandwidth for every transmit opportunity or every 10th transmit opportunity. Whichever way I do that, I'm going to make a decision of which one of yous I'm going to talk to first. So what I'm going to do is I'm going to send you out a trigger. And basically, I'm going to send you out a message saying, you get to talk next. You guys are going to send me back another message saying, cool, I'm ready to go. I'm going to send you another message, say go. Then you have to send it because you all have to use the same transmit opportunity. You all have to fill that same that field. If you have a little bit of less data, you actually have to put padding in, which is okay because that padding could be another packet. That padding could be more information. But everybody has to have information at the same level within that field. Then I'm going to send you a block ACK. This is kind of what it looks like, but looking at it a different way. Trigger 1, buffer status report poll. Who's got information to send? Buffer status report. We do. I'm going to make a decision who gets to talk to next. I'm going to send the trigger, multi-user request to send. You guys are going to say, cool, I'm ready to listen. Then I'm going to send a trigger, and within 400 nanoseconds, you guys all got to reply simultaneously. And you can fill the fields any way you want. And then I'm going to do a block ACK. Pretty cool, huh? This is kind of what it looks like at that point. And once again, this is talking to 4 people. I could talk to 7 people, as you could see in that one graphic I had, talking to 15 different people. So then this is the way it looks like, kind of in a more non-technical look. I just send this out, let you guys know what's going on. Then there's some other cool stuff. What if I didn't give you a transmit opportunity? What if I didn't give you a resource unit? What if you got information to send and I'm just not giving you a slot? There's something called uplink OFDMA random access. What I can do is I can put aside some resource units and say, by the way, I'm going to dedicate these 5 to the 5 of you, and the other 4, best effort. Standard Wi-Fi top operation. You know, pick a transmit opportunity, back off. You know, there's a standard back off, just like the same thing we have right now. I've got 4 fields in there. Take your best shot. If you collide with somebody else, neither one of you get an acknowledgement, you back off again and try again. So there is some additional functionality here. And there is some other stuff coming down the pipe. If you read that very last bullet, may allow unassociated stations to talk to the AP. Now, who ever heard of that? Maybe there's a station that's so far away that they can hear the access point because the power level of the access point, but the access point can't hear me. So maybe I can use one of these smaller channels with a higher power level and send messages. And if this seems really weird to you, don't let it, because there's a lot of discussions within the IEEE and the Wi-Fi Alliance about allowing clients to get information from an access point without actually being associated to that access point. If you follow any of the Hotspot 2.0 and Passpoint and stuff like that, there's some features already existing in there to allow you to do that. One of the other things, now some of you guys might have looked at that and said, my God, I gotta do a buffer status report poll, and then I got a buffer status, and then I figure out, and then I send a trigger, and then I send a CTS, and I gotta send a net. Is that really efficient? Well, if you look overall, it is, but there's also something else down the road. Once again, As I mentioned before, there's 682 pages in the IEEE document. There's 132 pages in the Wi-Fi Alliance, MRD. So not everything makes it from the one document into the other. It's important to understand that. So there's other thing called cascade mode. How do I even make this more efficient? So if you look at the top one, we talked about that already. If you look at the second line, we talked about that already. But what if I take this to the next level? If you look at the next level down there, within that transmit opportunity, I'm talking to and listening from clients. What I'm actually happening there, I get access, I got a preamble, kind of missing a trigger there, but I'm sending data down to stations 1, 5, 7, and 9. You guys will all reply with an acknowledgement, but some of you might actually add data as part of that acknowledgement, and there might actually be other stations just sending data on their own. So this is down the road, once again, whether it's 1 year, 5 year, 10 years, or never. The whole idea is I can cascade this, get rid of a bunch of triggers. You know, if I'm sending you a packet, instead of you just sending me acknowledgement, send me the data that you want to go upstream, because by you sending that, I'm assuming you acknowledge it. I'm assuming you got your data. So the whole idea as we go forward here, it's going to become much more efficient, much more useful as far as that's concerned. So kind of summarizing this thing a little bit, the AP controls everything. The AP controls uplink communication, the AP controls downlink communication. Right now, all that's really required within that is all I have to do is make decisions based on quality of service. So if I've got 15 people, 20, 30 people connected to the access point, and I'm allowing 9 resource units, I'll just use quality of service to decide who talks when. But once again, just like with airtime fairness or any of the other proprietary protocols out there, we can do whatever we want. Once again, it's going to be really, really cool in a mesh-type environment where I can nail up connections with some resource units and talk to others. Whereas right now, if I try to have a mesh connection and client connectivity on that same radio, I'm jumping back between them, and neither one are getting a good experience. So this is going to give me a much, much better experience. So once again, that's kind of really, really cool how that's going to work. The timeline, as I mentioned before, I kind of showed this. I'll put my marketing hat on just for a minute. We do have the APs. They're available now. Should you buy that? And I'm not going to go to the marketing right now, but several people said AC works. It's great. There's nothing wrong. Why should I go to AX? Is that a good? What do you think? Should you go to AX or stick with AC? If you buy AC today, that's all it's ever going to have. If you buy AX today, it's AC today and it's AX in the future. What we see in the industry right now is people turn over their phones about every 18 months, people turn over their tablets about every 24 months, and laptops every 36 months. Thank God for the younger generation, because they want a new phone every year. So we're going to see the transition to 11AX a lot quicker than most people think it's going to happen. Is it available today? The clients? No. Will they be available for the end of the year? Absolutely. Will you see large shipments next year? Absolutely. The way I position 11AX right now is if 5, 6 years ago I was going to go out and buy a TV. I bought a high-definition TV. There was one high-definition channel, but I knew they were coming. Same thing with 11AX. It's going to go that direction. So where we started, I want to talk about this just a little bit more. Is 11AX Wi-Fi switching? Devin says it is. I don't necessarily agree with him. Is it? Somebody say it depends. It does. Because it all comes down to what's a switch. And that's an important thing to understand. What is a switch? Got a question for you guys. Who thinks in this room they know what a switch is? Don't worry, I'm not going to ask you a question. Just let me see your hand. And pretty much everybody's going to put their hand up. Put your hand up if you think you know what a switch is. I'm not going to call on you. Promise. Okay, if you're under 50 years old, put your hand down, because you don't have a clue. I forgive you for your youth. Switching came out in 1989, 1990. And so if you haven't been around that long, you're probably not a good reference. Okay, the rest of you who had your hands up, if you do not know who Radia Perlman is, put your hand down. Because if you haven't read her book, Interconnections, you don't understand the bottom 3 layers of the OSI model. So the bottom layer here, so what is a switch and where does it fit? Everybody here read chapter 1 of a CWNA module book, hopefully. So within the OSI model, where does a repeater sit? Layer 1. It doesn't know about packets, doesn't know about frames, doesn't know about addressing. All it knows is a signal comes in, I clean off the noise, boost the signal, and send it on out. It's cool. Where does a bridge sit? Not a trick question. Bridge sits at layer 2. So I understand frames at this point. I do smart intelligent forwarding. I do all layer stuff. Great. Where does a router sit? 3. Good. I'm at the protocol level. I understand IP. I do the bridging. I do this. Where does a switch sit? It depends. I got layer 2 switch. I got 2 plus switch. I got 3 switch. I got 4. I got 7. If the switch fits in every layer, it doesn't fit anywhere. So that's why I told you guys if you're under 50, you got to shut up. Because a switch is a marketing term. It is not on the OSI model. It's nowhere. It's a marketing term. It can be whatever you want. So what's required to have a switch? What's required for something to do switching? What? MAC address. What technology? Communication path? Transparent bridging. Okay, what do you mean by single collision domain? Just 2 people talking. What's an extension of that? 2 letters, got an F and a D. A lot of people say in order to do switching, I need to do full duplex. Does anybody believe that? You're close, but 100% wrong. In order to do full duplex, you have to do switching. And it's important to understand, because once again, let's be honest, this is a little bit of marketing stuff. So what is the first switch ever made? What is identified as the first switch ever made? No. The Calpana 700. The Calpana EPS 700 came out in 1989. Does anybody in their right mind think this thing did full duplex? It had 7 AUI ports on it. Most of you guys are too young to know what that is. It's a 15-pin connector that goes to a transceiver that goes to a vampire tap that's stuck into a big, thick Ethernet cable. And it was $1,500 a port. This device is identified as the first switch on the market because it did exactly what he did, is that on a single media, on a single channel, I could have serial communication between 2 devices, and next door I can do 2 devices. There is no requirement for full duplex in a switched environment. So if that being the case, do resource units and OFDMA allowed me to do switching? You decide. It's a marketing thing. It's up to you. And by the way, the word Calpana, does anybody know where that came from? It's the founder's wife's name, and it means imagination and creativity. And that's what I'm going to lead you with. Don't necessarily follow anybody blindly. Think for yourself. And that's what they did. Is it Wi-Fi? I don't care if it's Wi-Fi switching. That's a marketing term. It's not going to make any difference to anybody else. But that's the whole idea. So OFDMA is really about allowing multi-user communication. Allow you and I to talk simultaneously while you and I are talking simultaneously. That's what OFDMA is all about. Is it going to be ready tomorrow? Absolutely not. Are we going to start seeing 11AX clients next year? Absolutely. Are we going to see large volume shipments of 11AX clients next year? Absolutely. I can't tell you who, but I can guarantee it's going to happen. That being said, I got 2 minutes left. Does anybody got any questions? I can't have been that good. Okay, sorry, it's hard to see the lights. Go ahead. Well, they're not obsolete because I figure there's going to be G clients long after I'm dead. You're going to have mixed environments. Once again, there's a lot of studies, and it's all paperwork studies that say you're really not going to start seeing the advantages of 11AX until you got about 20% 11AX clients on your network. There's always going to be a mix. But if I got 100 clients in my environment, and we're all talking, that's 100 contention periods. If 20% of those clients become 11AX, I just dropped that to 81 contention periods. If 50% of those clients become AX, I'm just down to 51 contention periods. It's going to become more efficient, but the more AX clients you have on the network, the more efficient it's going to be. Once again, we're going to have, as I said, G clients for the rest of our lives. They're not going away. There is no, some people say there's some advantage to legacy clients with 11AX. It isn't. You could say I got a higher performance chipset and spin it that way, but it really isn't. Anybody else? I must have done a great job if nobody's got questions. All right, thank you very much. I'll give you 39 seconds back.